Hello. Let's check if everything works. I think it does. Okay, looks like it. Cool. Okay, so today we will be talking about Mip-NeRF. Mip-NeRF 360 is an extension to the original Mip-NeRF paper. It came out about 9 months later compared to the first Mip-NeRF. And this method is basically taking whatever worked for Mip-NeRF and turning it into like unbounded scene representation. So the goal here is mostly to model the faraway area from the central object, right? So like here, the background objects usually come out blurry in original solutions, and Mip-NeRF 360 is creating a representation that will allow to render unbounded scene content beside the central object. So that's the main goal of this technique. Yeah, and they have quite a few tricks that they're gonna apply to make it work, and we will go through the paper to see it through. So let's get started. So this is our paper. Yeah, and let's start reading this. Okay. So this is Unbounded anti-alias neural Radiance Fields. This is related to the fact that Mip-NeRF is creating anti-aliased representation. So this is what we saw in the last stream. What else? Let's read the abstract first. Yeah, NeRFs struggle on the unbound scenes, meaning the scenes that have a lot of background space, especially the background space that can go into infinity. Yeah. Content may exist at any distance. This is the issue. In this setting, existing NeRF-like models often produce blurry or low-resolution renderings. Yeah, that's the case. They are slow to train, but honestly, all the Mip-NeRF solutions are also slow to train, so yeah, it may exhibit artifact to inherent ambiguity of the task of reconstructing a large scene from a small set of images. We present an existing extension of Mip-NeRF, great, that's from the same authors by the way, that uses a non-linear scene parametrization, online distillation, and a novel distortion-based regularizer. So these three things are basically the three tricks that they do in this paper to get the results. We'll go over them one by one. Blah, blah. Our model, which we dubbed Mip-NeRF 360, as we target scenes in which the camera rotates 360 degrees around a point. So these are the scenes that we saw in the video at the beginning. This reduces mean squared error by 57% compared to original Mip-NeRF and is able to reproduce realistic synthesized views and detailed depth maps for highly intricate unbounded real-world scenes, which sounds great on paper. So let's look at it. There is intro. Yeah, NeRF models the input of to the MLP using infinitely small 3D points along array, which causes aliasing. This is basically the idea they figure out in Mip-NeRF, where instead of rays they use cones. Yeah, exactly. But they both struggle with unbounded scenes, so that's what they're planning to solve here, where the camera may face any direction and the scene content may exist at any distance, right? In this work, we present an extension to Mip-NeRF we call Mip-NeRF 360 that is capable of producing realistic renderings of these unbounded scenes as shown in figure 1. Yeah, so this is the kind of scenes they want to deal with. So this is the original Mip-NeRF and this is their Mip-NeRF, and we see that there is a lot more depth here, depth detail, in this Mip-NeRF model than this. We can look closer. Yeah, we see that there is like some building here or something like that, and we don't have any windows here, and here we have like a detailed windows, and the building is clearly further away looking at this depth map. So that's great. So applying NeRF like models to large unbounded scenes raises three critical issues. We have parameterization issue. So unbound 360-degree scenes can occupy an arbitrarily large region with Euclidean space, so we cannot just assume some kind of cube. But Mip-NeRF requires that the 3D scene coordinate lies in a bounded domain. So most of these networks so far at that time required that, and this is a good assumption for simplicity in many cases, required to have like a specific cube, dome of space that we want to model the arrays in. And if you go outside of these cubes, you don't necessarily have to have a solution for the MLP, from the MLP that is meaningful. This is not the case for Mip-NeRF, because for Mip-NeRF you want to be able to sample points in an unbound length from the camera, right? So let's say 500 meters from the camera, we want to have some kind of result. So we cannot assume some cube. So this is the issue they're talking here. We don't have this kind of bounding box of the scene. So that's cool. We cannot have a bounding box, so that means we have to change some things, definitely, in parameterization. Then there is efficiency issue. Large and detailed scene require more network capacity, but densely querying a large MLP along each ray during training is expensive. I mean, that's kind of like, and NeRFs are not necessarily efficient kind of statement, which is of course true, but I don't think this particular solution in the end ended up being specifically efficient. But basically, if they do like unbounded scenes, if they do it very naively and just sample all their arrays and all the points whatever way, then it will be prohibitively expensive, like much even worse than the just training for 48 hours, meaning like training for a month. So that doesn't make any sense. And then there is the ambiguity issue. This is the idea that the content may lie at any distance, and if the content is observed only by a small number of rays or even a single ray, this will create more ambiguity in the reconstruction. So I'm very curious how they're gonna try to solve that, because inherently that's the data limitation, right? So if we just have some images that represent this 3D scene from which we are trying to extract the whole 3D representation, right? If the images are made in a way where, because the point is very far, there is only like one pixel that reaches this point, inherently we have a very low amount of data for that point, right? We only have this one pixel of training sample. So I'm very curious how do they try to deal with that here. Okay, parameterization, yeah. Due to perspective projection, an object placed far from the camera will occupy a small portion of the image plane, of course, but will occupy more of the image and be visible in detail if placed nearby. So that's very obviously what the perspective is. Nothing crazy. Therefore, any ideal parameterization of 3D scene should allocate more capacity to nearby content and less capacity to distant content. So that's the idea. So distant content, smaller, less important. We don't need that high resolution of it, that high understanding, so we will allocate network mostly to the frontal content and then allocate some level of capacity to the faraway content. Outside of NeRF, traditional view synthesis method address this by parameterizing the scene in projective panoramic space, by embedding the scene with content with some proxy geometry that has been recovered using multi-view stereo. One aspect of NeRF success is its pairing of specific scene type with appropriate 3D parameterization. The original NeRF paper focused on 360-degree captures of objects with masked backgrounds, and on front-facing scenes where all images face roughly the same direction. For masked objects, NeRF directly parameterize the scene in 3D Euclidean space, so that's usually the case. You just have the 3D bounded region. But for front-facing scenes, NeRF use coordinates defined in projective space, normalized device coordinates, or NDC. And by wrapping an infinity deep camera frustum into a bounded cube, where distance along the z-axis corresponds to disparity inverse distance. That's interesting. So they did some kind of reparametrization where they still get a cube, but it wasn't just like regular cube. The z-axis used this inverse distance metric to represent the distance in this one dimension that is like far away. So this NDC effectively reallocates the NeRF's MLP's capacity in a way that is consistent with geometry of perspective projection. Okay, so they say basically because the embedding of the input to the network is reparameterized, this will effectively force the network to learn in this way we want, which is this, it will like provide more, we'll still close it in like a cube, but it will provide more capacity in this local area, and then as the Z goes further it will have less capacity, I think. Wrapping the infinitely deep camera frustum into a bounded cube where distance along the z-axis corresponds to disparity inverse distance. Okay, cool. However, scenes that are unbounded in all directions, not just in single direction, require different parametrization. This idea was explored by NeRF++ paper, which is an additional network to model distant objects, and by NeRF, which proposed a space wrapping procedure to shrink distant points towards the origin. Okay, so that's what people do usually. They just have some kind of way to translate distant points to be closer to the origin, and they have like a ball around the origin that they really query. Both of these approaches behave somewhat analogously to NDC, but in every direction rather than just along the z-axis. Okay. In this work, we extend this idea to Mip-NeRF and present a method for applying any smooth parametrization to volumes rather than points. So what they mean by that is that I think they're gonna do the same thing. They're gonna shrink distant things closer to the origin, and they have this kind of mapping from like a distant point, any distant point, whatever distance away, into some kind of closed or near origin space. But the idea here is that Mip-NeRF, when we do that with Mip-NeRF, right? The Mip-NeRF, the whole point of Mip-NeRF was that you had these like Gaussians that had different sizes based on how far away they were from the camera, how big the frustum, which is this like cutted cone, was for this particular Gaussian. Then you had different representation, right? So the idea is if you just take away the points, that's easier, but now you have to move away the volumes into this cube, and then you have to change the volumes so that not only the position changes of the volume, but also the volumes probably have to shrink to fit into this ball. So they will just try to do the same thing that these two previous papers, but just try to keep this Gaussian volume representation that they build out for the regular Mip-NeRF to have the same kind of results. So they will present this kind of reparametrization, and they also say here like we present our own parametrization for unbounded scenes. So we'll see how they do that exactly. So the idea will be to bring the Gaussians closer to the origin in some closed space, and probably adjust them, probably shrink them to fit there accordingly to some equation, and we will figure out what they exactly do here. Okay, let's look at efficiency now. One of the fundamental challenges is that such scenes are often large and detailed. Well, yeah. NeRF can reproduce objects and regions of scene using surprisingly small number of weights. But the NeRF MLP saturates when faced with increasingly intricate, say, content. Additionally, larger scenes require significantly more samples along each ray to accurately localize surfaces. Yeah, for example, when scaling NeRF from objects to buildings, someone doubled the number of MLP hidden units and increased the number of MLP evaluations by 8x. Great. Even bigger thing. What happened just here? Yeah, that's not that. 8x, not fun. This increase in model capacity is expensive. A NeRF already takes multiple hours to train. Multiplying this time by an additional 40x is prohibitively slow for most users. Yeah, exactly. This training cost is increased by coarse-to-fine resampling strategy used by NeRF and Mip-NeRF. MLPs are evaluated multiple times in coarse and fine ray integers and are supervised using an image reconstruction loss on both passes. Yeah, so this is the idea. First course evaluation, you're trying to get an idea where the most density of the object is in the space, because we don't have density given a priori, right? So you just do some kind of uniform sampling, and then you have like a histogram or like general like a PDF of, you can trace back the PDF or where the most density likely is, and then you sample according to that PDF, and then you have this fine sampling, right? And they say this approach is wasteful as the coarse rendering of the scene does not contribute to the final image. Yeah, but it kind of does contribute, meaning like it contributes because it allows for correct sampling of the fine network or the fine evaluation. But yeah, in a way it doesn't contribute the color of the object, right? So maybe we can make it do it more in a smarter way. So let's see what is their smarter way. So they say instead of training a single NeRF MLP that is supervised at multiple scales, we will instead train two MLPs. Great. So now we have two networks instead of one. We have proposal MLP and NeRF MLP. The proposal MLP will be doing coarse, right? Predicts volumetric density but not color. Okay, right? Because we don't need color to build out this density PDF, right? And these densities are used to resample new intervals that are provided to the NeRF MLP, which then renders the image. Exactly. So basically, instead of doing this 2 times, they will have one network that is yielding this like base density, and then they will have the second network that is actually doing the full NeRF-like evaluation, which is only gonna do the fine level. So they're gonna use this PDF from this previous network, and then get like PDF of density, sample points from this PDF, use these sample points as an input to this NeRF MLP, query NeRF MLP at this input, and get the color and the actual color and density. So likely they're gonna say this proposal MLP probably can be smaller, and this NeRF MLP has to be big, and because it's smaller, it's faster, or something like that. So let's see. And these densities are used to resample new intervals that are provided to the NeRF MLP, which then renders the image, yes. And crucially, the weights produced by the proposal MLP are not supervised using the input image, okay, but are instead supervised with histogram weights generated by the NeRF MLP. So that's the big point. Now that's even smarter. So you know how to train NeRF, right? You have to get the rendered image from the NeRF and then subtract it from the actual image and use that as your loss and do backpropagation doing that, right? But to do that, you have to have all these pixels, right? You have to calculate all the pixels and then subtract and then do the backpropagation and do that again. So you need to query this NeRF a lot of times to just be able to do the training. But the point here is, so this procedure of like subtracting and calculating the backprop through the whole network and everything is very, very expensive. But their idea here is that, how about, you know, this proposal MLP, we don't have to do that for it, right? Because NeRF MLP is gonna be trained on this image, and this NeRF MLP will be trying to get some idea of the densities. And this proposal MLP, we just needed to approximate this density distribution in 3D. So that's what they say here. Instead of supervising this with this input image, they will use like a histogram of weights generated by the big MLP. So they will use like a big NLP as like a teacher for the smaller NLP, to approximate the histogram of the density, so meaning like the distribution, the PDF, or however you want to think about that. So we want to approximate the actual distribution. The actual distribution will come through this NeRF MLP, because NeRF MLP will be training from the images, but the proposal is only focused on approximating this distribution. And then at the inference time, this will make it better, because the proposal will give the estimate, and then the main NeRF MLP will sample around these points. This allows us to use large NeRF MLP that is evaluated relatively few times, yes, alongside a small proposal MLP that is evaluated many more times, yeah. So then when you have this, exactly, so then when you have this approximator, and we assume, let's assume this MLP, this proposal is already trained, we just put in uniformly sampled points many times and get very exact histogram, and then we use that to sample this NeRF MLP only once correctly, this big one. So yeah, so this sounds like a good idea. This is like a two-step process, but it sounds like a much faster process. Okay, let's do it further. As a result, our whole model's total capacity is significantly larger than Mip-NeRF, about 15 times, resulting in greatly improved rendering quality, but our training time only increases modestly 2x. Okay, so that's a good trade-off, I think. 2x for 15x sounds good. I don't know how they exactly calculated this total capacity, but let's believe these numbers are good approximate. Time probably is just measured. Okay, so let's see further. We can think of this approach as kind of online distillation, while distillation commonly refers to training a small network to match the output of an already trained large network. Here we will distill the structure of the output predicted by the NeRF MLP into proposal MLP online, okay, by training both networks simultaneously. Okay, that's exactly makes sense. So at the beginning, all of these networks will be random, right? But over time, this NeRF MLP will be getting the idea of where the density is, and as soon as this gets some ideas of where the density is, this proposal MLP will be trained to generate the same idea. So it will be producing approximation of this whatever is learning, this NeRF MLP is learning, right? So that's good. So they are distilling not the whole output, but they are just doing the distillation of the density here. Okay, then they talk about NeRF. NeRF performs a similar kind of online distillation for entirely different tasks, training MLPs to approximate rendering integrals for the purpose of modeling visibility and indirect illumination. So they took this idea from this paper, apparently. Our online distillation approach is similar in spirit to the sampling oracle networks used in NeRF, though that approach uses ground truth depth for supervision. Okay, so NeRF is using ground truth depth, and we don't have that. That would make everything much easier. A related idea was used in Mip-NeRF, that though that approach only accelerates inference and actually slows training, okay, a NeRF is trained to convergence and an additional network is trained afterwards. So yeah, that makes sense that it slows, right? Because you have additional step later. They are just like, instead of doing that later, let's do it online while we are training, and let's sample this main NeRF using this proposal. So that's eliminates a lot of sampling of this big NeRF. A learned proposed network was explored in NeRF in detail, but only achieves speed of 25%, while our approach accelerates training by 300%. Sounds great. Accelerates training 300%. Sounds amazing. Several works have attempted to distill or bake a trained NeRF into a format that can be rendered quickly, but these techniques do not accelerate training. The idea of accelerating ray tracing through a hierarchical data structure such as Ox trees or bounding volume hierarchies is well explored in the rendering literature, though these approaches assume a prior knowledge of the geometry of the scene and therefore do not naturally generalize to an inverse rendering context in which the geometry of the scene is unknown and must be recovered, right? That would be great. If we knew that where the geometry is, how the problem is solved, right? So then we can just like sample around this geometry, and that would be great, but we don't, so we cannot use these techniques. Indeed, despite building on octree acceleration structure while optimizing NeRF-like models like neural spurs, voxel fields approach does not significantly reduce training time. Yeah, so this is a good approach, but it doesn't really improve training that much. And honestly, their model will be kind of still slow, so it also doesn't do much. But it's a smart idea to do this kind of online distillation. So that's very interesting. Okay, ambiguity. Though NeRFs are traditionally optimized using many input images of a scene, the problem of recovering a NeRF that produces realistic synthesized views from novel camera angles is still fundamentally under constraint. Okay. An infinitely small family of NeRFs can explain away. An infinite family of NeRFs can explain away the input images, but only a small subset produce acceptable results for novel views. Yeah. That's the issue. This is this kind of like 3D collapse. For example, NeRF could recreate all input images by simply reconstructing each image as a textured plane immediately in front of its respective camera. Yeah. The original NeRF paper regularized ambiguous scenes by injecting Gaussian noise into the density head of the neural MLP before the rectifier, which encourages densities to gravitate towards either 0 or infinity, right? So this was this original way to remove floaters from NeRF. Though this reduces some floaters, exactly by discouraging semi-transparent densities, we will show that it is insufficient for our more challenging task. Other regularizers for NeRF have been proposed, such as robust loss on density or smoothness penalties on surfaces, so that's more on the SDF side. But these solutions address different problems than ours, slow rendering and non-smooth surfaces respectively. Additionally, these regularizers are designed for the point samples used by NeRF, while our approach is designed to work with the continuous weights defined along each Mip-NeRF ray. So this is the another, like, the point is, again, we want to work on these Gaussians instead of just these points. These three issues will be addressed in section 2, 3, and 4 respectively. After a review of Mip-NeRF, we will demonstrate our improvement over prior work using new dataset consisting of changing indoor and outdoor scenes. We urge the reader to review our supplementary video. Yeah, watch the video. Awesome. Okay, so now we will go over the Mip-NeRF. So if you want to understand Mip-NeRF in detail, we have the whole stream about that on my channel already. In this series of implicit neural rendering. But we will go over this section here and see how they explain Mip-NeRF again. So let's see. Let us first describe how fully trained Mip-NeRF renders the color of a single ray cast into the scene R of t. And this is origin, this is the displacement along the, this is the length t along the displacement d, direction of the ray respectively, t denotes distance along the ray, exactly. Yeah, so this is RT. In Mip-NeRF sorter vector of distances t, t is defined, sorted vector of distances t is defined, and the ray is split into a set of intervals ti. So these are the intervals between this vector, these distances in this vector. For each interval I, we compute the mean and covariance. So this is this Gaussian representation. Mean and covariance of this particular interval, right? So this is the interval for the I of the canonical frustum corresponding to the interval, the radii of which are determined by the ray's focal length and pixel size on the input image plane. So this is basically this mean vectors and covariance vectors for all these Gaussians along this different ti to ti plus 1 spaces defined in this vector of distances, right? So we'll have this mean and covariance matrix for all of them, for all of these 3D Gaussians. Yeah, and those Gaussians are of course fitted to this, like the size of the cone there, right? Okay. And featureize these values using the integrated positional encoding. This is the main idea of the Mip-NeRF paper, right? So this is the integrated positional encoding where you have this additional term here, right? Other than the regular kind of positional encoding, you have this term that depending on the diagonal part of the covariance matrix will shrink the representation or expand it. So it will shrink the representation for the bigger Gaussians, so that we have less features. And this basically allows you to reason about how big is this 3D volume that right now I need to approximate with my NeRF. Is it small volume? Is it big volume? Is small because it's close to the pixel? It's big because it's far away from the pixel. So this is the term that is solving that issue. And this is also the expectation of the encodings used by NeRF with respect to the Gaussian approximating the canonical frustum. So this is the whole idea. These features are used as input to MLP parameterized by the weights of these weights, right? That outputs density and color. Yeah, so for all of these intervals, for all of these intervals, we can render them. We can basically what we do for all of these intervals, we put them into this encoding, right? And then we have this positional encoding, and we apply our parameters for the NeRF, and we get for all of the intervals we get the density and color. And the view direction is also provided as input to MLP, but we omit this for simplicity, right? Because for most NeRFs, and this is also the case for Mip-NeRF, you provide this view direction, different form, but usually as a theta and phi in the as input as in the original NeRF. You provide that in the close to the last layer at the end of after you already extracted density. You provide that to allow for estimating any specular effects, any view dependent effects, so like the lighting conditions that change based on the camera position and things like that. So you allow this additional level of disambiguity, yeah, conditioning on this view direction. So this is a typical thing. They don't put that here, but that's also the case. With these densities and colors, we approximate the volume rendering integral using numerical quadrature. So this is our standard integration of the color for the pixel. We just take the weight and we multiply it by the color for all of these intervals, and this weight is calculated using this our density here. This is how we extract this particular weight value depending on the density estimation and the size of the interval here, right? That's great. And this is the final rendered pixel color, right? Cool. By construction, the alpha compositing weights W are granted to sum to less than or equal to 1. Because of this calculation here, the array is first rendered using evenly spaced coarse distances. So that's the idea, right? So usually you have these coarse distances first, which are sorted samples from a uniform distribution spanning T and TF. So this is our bounded region, right? So you have our bounded region. From when we have like a bounded region, we have the T and TF. This is the beginning, this is the end of the region, and we just sample along this space and we sort them. And this is this uniformly sampled points. So this is nothing crazy here. This is just our assumption. And then during the training, this sampling is stochastic, but during evaluation, samples are evenly placed from Tn to Tf. Okay, cool. After the MLP generates a vector of coarse weights Wc. So this is this first vector that gives us a general idea where the density actually is in the space. Fine distances Tf are sampled from the histogram defined by Tc and Wc using inverse transform sampling. So this is the idea, right? This is the idea where we first sample uniformly, get general idea where the density is, and then we resample. We resample with this Tf. And we get this TF based on these densities Wc. So they describe it here like that. Because the coarse weights Wc tend to concentrate around sin content, this strategy improves sampling efficiency, right? Because we're gonna sample around wherever the most density is. A Mip-NeRF is recovered by optimizing MLP parameters this theta NeRF via gradient descent to minimize weighted combination of coarse and fine construction losses. So in Mip-NeRF we have this, this is the first loss, this is for the uniform sampling because you see the C here, right? And there is the final sampled loss, and this is divided by 10 for a good measure to really focus on the main loss, not on the coarse loss. This is just to provide gradient to the uniformly sampled points, right? But they are much less important than these correctly sampled points around the density. And the R is the set of rays in the training data, and this is our ground truth color corresponding to the ray R taken from an input image, and the L recon is mean squared error loss, right? So this is mean squared error between the color of the pixel and the color of the reconstructed pixel. Cool, let's go further. Scene and ray reparametrization. Though there exists prior work on parametrization of points for unbounded scenes, this does not provide a solution for Mip-NeRF context in which we must reparametrize Gaussians. Yeah, so this is the idea. If we would just move the Gaussians by moving their 3D mean, so the central point of the Gaussian, great, then we are the same as moving points. But in our context, because we want to have this property of understanding the volume size that we are actually modeling here, we want to be able to also modify, I assume, covariance of the Gaussians, and basically the size of the Gaussians in 3D, so that they fit into this some bounded region after we move the central point of the Gaussians, right? So that's what they will discuss here probably. So to do this, first let us define f of x as some smooth coordinate transformation that maps from Rn to Rn. So this is what we said. We're gonna map from probably infinite x to some bounded x in a moment. We can compute the linear approximation of this function. So this is a typical linear approximation with Taylor series here. And this is the Jacobian calculated at the input point, which is we can apply to f. And yeah, because we have this encoding here that we are using, we have to apply this reparametrization of this Taylor series like here to our encodings for all of these spaces, right? So we take that as input and we calculate. So this function will be fine, same thing as usual for the point. But then, as I said, we do this part here where we recalculate our sigma based on the local Jacobian around these points that we are translating, right? And they know that this is functionally equivalent to classic extended Kalman filter, which I personally don't know what that is, but I don't think that's the big issue. The whole point is we're gonna probably shrink these Gaussians to fit into this ball here, where f is the state transition model. Our choice of f in the following contraction, right? So we need to contract to fit into the space. So we have this. Okay, so if the x is smaller than 1, we keep it unchanged. But if this x is greater than 1, we have this contraction here, and this will allow us to, if I read that correctly, to always be in between 1 and 2. Of course, like -1, -2 as well, right? So basically we'll have a ball of radius 2 around the origin, and all the points that are above 1 will always fit between 1 and 2 radius. Yeah, as you see, this is the this divergence from yeah. So the no matter how big this is, this will always be under 2, because the bigger x is, the smaller is this this term here. But no matter how small it is, it will be always smaller than 2, and this is just making sure we change the sign correctly. Yeah, because this is either 1 or -1. Okay. This design shares the same motivation as SDC. Distant points should be distributed proportionally to the disparity inverse distance rather than distance, right? So instead of just increasing this by the distance, we subtract this inverse distance here. In our model, instead of using Mip-NeRF's IPA features in Euclidean space as per equation 1, we use similar features, see appendix. Okay, we will. I assume it's nearly the same thing. We use this in this contracted space where we have this, we first contract this Gaussian and then we encode. See figure 2 for a visualization of this parametrization. Let's see figure 2. Okay. Oh yeah, this is great. So let's read the figure 2. What's going on here? So I assume these arrows are basically the contraction. This is like a field that is affecting all the space around. This is unaffected domain is blue. So this is the radius 1 where we just don't change anything. And this is the contracted domain, and as you can see, its radius is 2 here, so that's how I calculated that before. That's great. And then we have contracted Gaussians and Euclidean Gaussians. So if the camera is here, the Gaussians go like that, and if we had like a regular Mip-NeRF parametrization, we'll just have these Gaussians here that we will input into the encode with our features and input into the MLP. But instead, if we have the contraction, we will have these Gaussians here, and we will still, all of them, no matter how many of them are there, we will fit them around this ball here. We will fit them here. Same thing for this one, I assume, right? So we have these Gaussians here, and because the camera is, by the way, camera is coming outside of this region, it's just having these Gaussians like that around the ball, and it's go there. And it's regular Gaussians in the middle of this blue one, but it's going around. And if it's going from the ball, it's unaffected and then contracted again in this ball to fit into this, into the maximum radius of 2 here. So that's very cool. Let's see this, what they say here. We define contract operator, shown as arrows, that maps coordinates onto a ball of radius 2, where points within radius 1 are unaffected. We apply this contraction to Mip-NeRF Gaussians in Euclidean 3D space. Gray ellipses are similar to Kalman filter to produce our contracted Gaussians, whose centers are guaranteed to lie within a ball of radius 2. The design of contract combined with our choice to space ray intervals linearly according to disparity means that rays cast from a camera located at the origin of the scene will have equidistant intervals in the orange region as demonstrated here. So I think they say that because the way we created this construction combined with our choice to space ray intervals linearly according to disparity. I don't know if we discussed that yet, but they say here they will space ray intervals, so they will space, I think, these intervals linearly based on 1 over x instead of x. That means that rays cast from camera located at the origin of the scene will have equidistant intervals in the orange region. So they say the distance between the centers of these Gaussians here will be the same because the camera is at the origin. I think this is the visualization for that part. That's cool. Okay, let's go further. In addition to the question of how 3D coordinates should be parameterized, there is the question of how ray distances t should be selected. Oh, so now they will discuss this. In NeRF, this is usually done by sampling uniformly from a near and far plane as per equation 5. So this is the idea. You sample from this beginning and end of your bounded region, but we don't have bounded region here, so we have to figure out something else. However, NDC, if an NDC parameterization is used, this uniformly spaced series of samples is actually uniformly spaced in inverse depth. This uniformly spaced series of samples is actually uniformly spaced in inverse depth disparity. This design decision is well suited to unbound scenes when the camera faces in only one direction, but is not applicable to scenes that are unbounded in all directions. Okay, so the idea is if you have this reparametrization with this z parameter that is being 1 over z, you just sample over 1 over z, which basically gives you the same results as if you sample like regular 3D equation, right? But it doesn't work here because we have this reparameterization not just in z direction but in every direction, so they will discuss their own version of that. Blah blah, but it's not applicable to systems that are unbounded in all directions. Exactly. We will therefore explicitly sample our distances t linearly in disparity. So they will sample linearly in 1 over x or like 1 over z or whatever the coordinate is, instead of sampling it in t. So usually we sample from t to t, and now we will sample from 1 over x to 1 over x. And they refer to some paper here that they give the spacing they get the spacing from, and this parameterized array in terms of disparity we define an invertible mapping between Euclidean rate distance t and normalized rate distance s. Okay, so we have this Euclidean rate distance t is our regular distance, and s is this normalized rate distance. It's normalized for this contraction here, so let's see how do they normalize that. So g is some sort of invertible scalar function, and this will give us rate distances of s from 0 to 1 that map to tn to tf. Okay, so we have tn, tf, tn, tf, we have s. So if s is 0, we get if s is 0 we get tn, if s is 1 we get tf. This is how this works. So this will just allows us to translate from 0 to 1, so this is why this is normalized, because 0 will be mapped to tf, to tn, sorry, and tf is mapped to 1, so 0 is at the beginning of our tf and 1 is at the end of our tf, and then this is all put into this g function. So g function will give us this will give this like disparity, right? This is the invertible scalar function, so this will be 1 over x, or this is it is 1 over x. Okay, let's raise it further. Oh, and this is the normalized distance, because we just put this we just normalize it over the whole region, over the given region. Okay, but I said, okay, throughout this paper we refer to distances along array in either t space or s space, depending on which is more convenient and intuitive. Okay, by setting g of x over 1 over x and constructing ray samples that are uniformly distributed in s space, and constructing ray samples that are uniformly distributed in s space, so this 0 to 1, we produce ray samples whose t distances are distributed linearly in disparity. Yeah. Additionally, setting gx equals log of x yields NeRF logarithmic spacing, but we don't do that, right? This is not for us. In our model, instead of performing the sampling in equation 5 and 6 using t distances, so where is this? 5 and 6. Oh, this is 5 and 6. Okay, so instead of doing in the t distance here, we'll do this in the s distance. So we will get this sampling that is not based on the far and close plane Euclidean distance, but will be from 0 to 1 in this 1 over x distance, which will give us the actual resampling for the cube. No, not cube, sorry, for the ball. Reduced to, yeah. Okay, let's get back here. This means that not only our initial sample is spaced linearly in disparity, but subsequent resampling from individual intervals of the weights W will also be distributed similarly. As can be seen from the camera in the center of figure 2, this linear in disparity spacing of ray samples counterbalances contract. Effectively, we have co-designed our scene coordinate space with our inverse depth spacing, which gives us a parameterization of unbounded scenes that closely resembles the highly effective setting of the original NeRF evenly spaced ray intervals within a bounded space. Yeah, so effectively, even though the actual positions we are using, like the actual things we are modeling, can be unbounded, we contracted them into this ball, and now because we have this respacing with the S, and we sample around this disparity, we're actually still sampling uniformly, but for the ball, So this basically works as like, oh, we had this Euclidean version, but it was unbounded. So now we close it into a ball, and it works again in this bounded ball. But in practical sense, we can put in any kind of input we want, but we still will be fitted in this space. So this will allow us to model just the points in the ball, so we don't have to have infinite capacity of the NeRF to model anything outside of unbounded region, even though we can input anything outside of unbounded region. So that's a very smart thing. Yeah, I like that a lot. Okay. What's next? Course to find online distillation. So that will be the idea for this proposal network. As discussed, Mip-NeRF uses a course to find resampling strategy in which MLP is evaluated once using coarse range intervals, again using fine range intervals, and is supervised using an image reconstruction loss at both levels. Yes. Mean-state training to MLPs, NeRF MLP, and proposal MLP. The proposal MLP predicts volume metric density, which is converted into a proposal weight vector W according to equation 4, but does not predict color. Yeah, these proposal weights is used to sample S intervals that are then provided to the NeRF MLP, which predicts its own weight vector W and color estimates for use in rendering an image. So this is our approximated, and this is our correct density for each interval. Critically, the proposal MLP is not trying to reproduce the input image, but is instead trying to bound the weights W produced by the NeRF MLP, right? So this is the idea. We don't use reconstruction loss here for the image. We're just gonna use some kind of distillation procedure. Both MLPs are initialized randomly and trained jointly, so this supervision can be thought of as kind of online distillation of the NeRF MLP's knowledge into the proposal MLP. We use a large NeRF MLP and a small proposal MLP, this is crucial, and repeatedly evaluate and resample from the proposal MLP with many samples. Some figures and discussions illustrate only a single resampling for clarity, but evaluate the NeRF MLP only once with smaller set of samples, right? So we're just gonna resample this proposal MLP, and then we're gonna evaluate the NeRF MLP at the end, based on the like kind of like a weight vector, or like not vector but like PDF for different regions. This gives us a model that behaves as though it has much higher capacity than Mip-NeRF, but is only moderately more expensive to train. Oh. Okay. Getting a fucking allergy. Give me 1 second. Okay, we're back. Okay. So getting back here. Okay, blah blah, where we finished? Okay, this gives us a model that behaves as the it had much higher capacity than Mip-NeRF, but it's only moderately more expensive to train. That's great. As we show, using a small MLP to model the proposal distribution does not reduce accuracy, which suggests that distilling the NeRF MLP is an easier task than view synthesis, which is probably true. This online distillation requires a loss function that encourages the histogram emitted by the proposal MLP. So this is our histogram, this is our amount of weight, which comes from the density for the specific region. And the NeRF MLP to be consistent, right? So we want this to align with the actual NeRF MLP histogram. At first, this problem may seem trivial, as minimizing the similarity between two histograms is a well-established task, but recall that the bins of these histograms T and let's say T prime or whatever you read that need not be similar. Indeed, if proposal MLP successfully calls the set of distances where scene content exists, this T and T will be highly dissimilar, right? So the idea is the bounds of the regions may be different for the NeRF MLP and for the proposal MLP. So we don't know the bounds, right? Specifically, this MLP here is like uniformly sampled, and this supposed to be have bounds only really within this density space. So these bounds are different. We just want to have such that, like, if you align it on top of each other, the weights aligned for these bounds are correct with the weights aligned for the bounds that are in the same space. So that's the difficulty here. Though the literature contains numerous approaches for measuring the difference between two histograms with identical bins, our case is relatively unexplored. This problem is challenging because we cannot assume anything about the distribution of content with one histogram bin. An interval with non-zero weight may indicate a uniform distribution of weight over the entire integral, a delta function located anywhere, or myriad other distributions, right? So if we had like a particular, let's say this kind of like a bin here, right? And this is our uniform distribution bin. Then if we have like a multiple bins inside for NeRF MLP, this might be that like all of them are the same, might be one is like very big, the other is very small. We don't know. We therefore construct our loss under the following assumption. If there is any way possible that both histograms can be explained using any single distribution mass, then the loss must be zero. So if there is a way for the NeRF MLP to have such a distribution inside that the this uniformly sampled distribution makes sense for it, then that's great. A non-zero loss can only be incurred if it's impossible that the both histograms are a reflection of the same true continuous underlying distribution mass. Okay, so if there is like, you cannot, if let's say NeRF MLP has a lot, and then all of these allots, if you sum them together, right, and they are their bounds together are outside of the, let's say, the one bin for the uniform distribution, but this one bin of the uniform distribution is has a smaller size than the sum of all of these things inside of it, inside of the same interval, then that's the problem, right? Because there is no way for this to be correct. They have some visualizations in appendix, so let's see, that's gonna help me explain what's going on here. Oh, this will be it probably, right? I assume. Visualization of the motivation behind this loss used to train our proposal MLP to bound the weights omitted by NeRF MLP. In both plots, we have two different histograms, TW shown in orange and TW shown in blue, generated from points X and X respectively, as well as plot of the bound described in the paper. If X equals X, the bound implied by TW is guaranteed to be an upper bound on TW, and our loss must be 0. If X is different than X, in this case only 16 of 20 points are shared between X and X, then TW may exceed the upper bound implied with TW and loss may be incurred. From this we see how minimizing LPROP encourages the proposal weights to describe the same distribution as the NeRF weights, despite their histogram being endpoints being different. Okay, let's see. So part A, X equals X. So, okay, the points here are like the ends of regions. This is the bound. This is TW, and this is our approximate. So orange is the approximation. So the orange is giving like here, the oranges, and there is the orange here, and orange here, here, here. And this is the actual thing, and this is the bound that we calculated. So because there is, for example, nothing here, then we have to have 0 here, right? Because there is no blue here, and this is the end is the same here. But here, for example, right, there is so little here that, like, if there is this little here to here, and the blue says that there is a lot more here, then we can have that much. If we sum this together on top of each other, we have that much. Sum this plus this, but we can have even more than that. Yeah, that's cool. So we have loss from this and this detail here. Okay. Very complex picture, honestly. Okay, where did we finish? So this is the bound. First we can define a function that computes the sum of all proposal weights that overlap with interval t. So for interval t, if the two histograms are consistent with each other, then it must hold that wi, so the actual thing, is smaller than the bound for all intervals ti, tw in tw. So if we have so we put in this interval here, we calculate the weight here, and we sum it for all the intervals who are in this tw. This property is similar to additivity property for an outer measure in measure theory. Our loss penalizes any surplus histogram mass that violates this inequality and exceeds this bound. So if there is more wi, more actual density than our bound calculated for all the intervals that are aligned with this, so going outside of this bound, then there is this issue, there is the loss. This loss resembles a half-quadratic version of the chi-square histogram distance that is often used in statistics and computer vision. This loss is asymmetric because we only want to penalize the proposal weights for underestimating the distribution implied by the NeRF MLP. So if there is, we only penalize it if we like, proposal MLP says, okay, it will be about X, and the factual loss from the NeRF MLP is much bigger. The distribution implied by NeRF MLP, overestimates are to be expected as the proposal weights will likely be more coarse than the NeRF weights and will therefore form an upper envelope over it. The division by wi guarantees that the gradient of this loss with respect to the bound is a constant value when the bound is 0, which leads to well-behaved optimization. Because t and t hat or whatever are sorted, equation 13 can be computed efficiently to the use of summed area tables. Note that this loss is invariant to monotonic transformation of distance c, assuming that w and w hat have already been computed in t-space, so it behaves identically whether applied to Euclidean rate distances or to normalized array s distances, okay? So that works for both, great. We impose this loss between the NeRF histogram and all proposal histograms. The NeRF MLP is supervised using reconstruction loss with the input images. As in Mip-NeRF, we place a stop gradient on NeRF MLP's output t and w when computing L-prop. Okay, so we see that NeRF MLP leads, the proposal MLP follows. So the idea here is that we don't change the Mip-NeRF, the main NLP, we don't change the main NLP to make L-prop smaller. We only make L-prop smaller by changing only the proposal MLP. So this way, we don't harm the training of the NeRF MLP. Otherwise, the NeRF MLP may be encouraged to produce a worse reconstruction of a scene so that to make the proposal MLP job less difficult. Yeah, so we don't want that. The effect of this proposal supervision can be seen in figure 4, where the NeRF MLP gradually localizes its weights W around the surface in the scene, while the proposal MLP catches up and predicts coarse proposal histograms that envelops the NeRF weights. Figure 4. This is a figure 4. Great. Okay, so this is looking at the whole space, we see that this is like randomly initialized. So these are our proposal, this is our NeRF, so it's like uniformly randomly initialized. And then 4% optimized, we see that all the density is mostly in this region, close to the surface, and the NeRF is like showing this kind of delta function here with some additional mass here, and histograms are trying to approximate this over here. And then when it's 100% optimized, we just have these two bins here, and this one bin, second bin, and this one is like more complex here, and this one is the actual NeRF function that is looking like that. So it's actually starting here. Interesting. Visualization of histogram TW emitted from the NeRF MLP black and the two set of histograms emitted by proposal MLP yellow and orange for a single ray from our dataset by Salkesin from over the course of the training. Below we visualize the entire ray with fixed X and Y axis, but above we crop both axes to better visualize details near scene content. Histogram weights are plotted as distribution to integrate to 1. When training begins, all weights are uniformly distributed with respect to ray distance t. As training progresses, the NeRF weights begin to concentrate around the surface and the proposal weights form a kind of envelope around the NeRF weights, so this is the case here. That's cool. So now we can just use this like the proposal network to get these distributions that are the colorful one, and then based on that resample the main one to get the final densities, which is great. And now they introduce the regularization they talked about at the beginning. So we also have the last component, the regularization. So we already discussed the main component, which is this contraction and new space sampling, and now we will go into the regularizer after we discuss this proposal network. Okay, so let's go to the regularizer. So due to ill-posedness, trained NeRFs often exhibit two characteristic artifacts we will call floaters and black background collapse, both shown in figure 5. By floaters we refer to small disconnected regions of volumetrically dense space which serve to explain away some aspect of subset of input views, but when viewed from another angle look like blurry clouds. By background collapse we mean phenomenon in which distant these surfaces are incorrectly modeled as semi-transparent clouds of dense content close to camera. Here we present a regularizer that, as shown in figure 5, prevents floaters and background collapse more efficiently than approaches used by NeRF or injecting noise into volumetric density. Okay. Our regularizer has straightforward definition in terms of the step function defined by a set of normalized ray distances S and weights W that parameterize such a ray. So this is the regularizer. Let's see what it does. Where WSU is interpolation into the step function defined as SW at U. Okay, so this is our step function. So it's either a weight if the U is there or not. We use normalized ray distances S because using T significantly upweights distant intervals and causes nearby intervals to be effectively ignored. Yeah, so S is like uniform in our parametrization, and T would be growing all the time if we just have some background point. So we want like uniform distances. So that's better. This loss is the integral of the distance between all pairs of points along this 1D step function. Integral of the distances between all pairs of points along this 1D step function scaled by the weight W assigned to each point by the NeRF MLP. We refer to this as distortion, as it reassembles a continuous version of the distortion minimized by k-means, although it could also be thought of as maximizing a kind of autocorrelation. This loss is minimized by setting W0. So if weight is 0, that's great. Recall that W sums to no more than 1, not exactly 1. If that is not possible, if the array is not empty, it is minimized by consolidating weights into as small region as possible. Okay, so we will push density closer together. Figure 6 illustrates this behavior by showing the gradient of this loss as a toy histogram. So this is the U and V is the positions of different points along the space, and this is the distance between these points, and we increase the distance by the basically the weight at this particular point. So we want the points that have weight to be close together so that this number is small, but if there is little weight, then we don't care that they are far away. But if there is a lot of weight between them, we want them to the distance between the points that we integrate to be very, very small. So let's see here. So this is the figure 6. So this is the visualization of the gradient of distance loss, the gradient of a regularizer, distortion. That would be distortion, right? That's how they call it, distortion. Yeah, okay, not distance. The gradient of our regularizer as a function of S and W on toy step function. Our loss encourages each ray to be as compact as possible by minimizing the width of each interval and pulling distant intervals towards each other, consolidating weight into a single interval or a small nearby number of nearby intervals, driving always towards 0 when possible. Okay. So we want to minimize the width of each interval, so make it smaller here, because of the S. So if the S is smaller, right? S is smaller, this distance will be smaller. So if the distance is smaller, then that's great, that's loss is smaller. Then pulling distance intervals towards each other. So for example, this is here, right? So we want to push it this way so that this U minus V is smaller as well, so this loss is smaller then. Consolidate into a single interval, small number of intervals, exactly. So if we just make it one integral, right, then again this is smaller. Driving always towards 0 when possible. Yeah, so this is the, I think this is W, right? So if the weights are getting smaller and smaller, even if the distances are high, if this is going smaller every time, right, this is getting smaller all the time, then the orange one, right, if all of these are going down, then that's better for us. And at the same time, like if we can just increase here and decrease here instead, like we can exchange that, then that's also like it's gonna lower the loss. That's very good. So the point is to force our mass distribution to be more of a delta function, more of a like a sharp delta function if possible, at a particular point, not just distributed along the distance. So we just kind of compact densities together, and when we compact densities together, we get like more sharp surfaces, and also less of these like artifacts where you have like a little bit of density floating in the space, right? So this is really good. Let's see. The equation 14 is straightforward to define. This is non-trivial to compute because WS has a constant value with in each interval. We can rewrite equation 14 as, this is the actual computed version, right? So this is the difference between this middle of this interval, middle of this interval. This is the difference, and this is just the difference inside of the one interval. And these are the weights for them. So this is the middle of the interval, this is the difference between the center of two intervals. In this form, our distortion is in trivial to compute. This reformulation also provides some intuition for how this loss behaves. The first term minimizes the weighted distance between all person interval midpoints, exactly. And the second term minimizes the weighted size of each individual interval. Yeah. So this is the size, this is the weight on it. Great. Optimization. Oh, this is the comparison. So you see that all of these black points is like a very close to camera floater kind of artifact that is helping with a particular view but not really helping with the scene. And if we have this LD stance loss that is pushing all the stuff to be combined spatially, this is very helpful. So yeah, I like that a lot. Okay, optimization. Now that we have described our model components in general terms, we can detail the specific model used in all experiments. We use a proposal MLP 4 layers and 256 units per layer, I assume, and NeRF MLP with 8 layers and 1024 hidden units. Yeah, so it's much bigger. It's 4 times bigger and then 2 times more layers. both with ReLU, internal activation, soft plus activation for density. We do 2 stages of evaluation and resampling of the proposal MP using 64 samples to produce each using 64 samples to produce these 2 histograms, and then 1 stage of evaluation of a NeRF MLP using 32 samples to produce SW. And we minimize the following loss. So this is our distortion loss, this is the regularizer, and this is our proposal MLP loss that is gonna bring the these 2 kind of like these histograms here from the proposal to the actual histogram. We have only K0 and K1, so not that much of this proposal, so that's evaluator, so that's not that much effort. And this is average all arrays in each batch. Arrays are not included in our notation. The hyperparameter lambda balances our data term reconstruction, loss reconstruction, and our regularizer loss distortion. This is the value that they use, so very typical. The stop gradient used in LPROB makes the optimization independent from the optimization of NeRF, and as such there is no need for the hyperparameter to scale the effect of LPROB, because this LPROB does not affect the NeRF, it's only affecting the proposal, so you want to 100% to affect proposal network, nothing else affects proposal networks. For reconstruction loss, we use Harbonnier loss, which is similar to which is slightly more stable optimization than mean-squared error used in Mip-NeRF, but it's very similar. It actually looks kind of like mean-squared error, but has also like this epsilon term here, and it's taking the square root of it, so it's a little bit different, but kind of the same. We train our model and early report a NeRF-like message in a slightly modified version of Mip-NeRF learning schedule. So this is the learning schedule and of all details of the warm-up and everything, so that's not very interesting, but if you're kind of interested to look at it, here it is. Yeah, so now there are results only, limitations and conclusions. We will go over the sections very briefly. We will look out through the appendix, but yeah, let's get over this quite quickly, so let's move on. They do 9 novel dataset, 9 scenes. Okay, they compare to all of these different methods. Numerically they are better usually, other than the stable view synthesis method, which is also pretty good. And this stable view synthesis method is a non-NeRF model that represents the state-of-the-art of a different view synthesis paradigm in which neural networks are trained on external scenes and combined with a proxy geometry produced by structure from motion. So that's interesting. I don't know much about this model. I don't think it's state-of-the-art anymore, but it was at the time, so that's interesting. We additionally compare with the public level with Zibur implementation of deep blending, blah blah blah. So they have a lot of these comparisons. We also present a variant of our model in which we use latent appearance embeddings. So this is typical for NeRF in a wild. This is the NeRF-W paper, which ameliorates artifacts caused by inconsistent lighting conditions during the scene capture. So this is like if you have multiple timestamps at which you capture the scene because you are walking around with the phone, right? You're gonna have different kind of effects that are only for that particular view. You want to disentangle them from the scene. And that's how the NeRF-W do it, is having this additional latent appearance embeddings. So they talk about different comparison, they talk about ablation study, they talk about how the removing IP completely using NeRF positional encoding reduces performance, showing the value building upon Mip-NeRF instead of NeRF. That's how they that's why they did this paper, basically, is that they want to keep these IPE features, these integrated positional encoding features compared to the regular features. But, you know, I think big part of this paper is, okay, they need to adapt to these Gaussians, but basically they just do this contraction, they do this proposal network, which helps, and they do this regularizer, and the regularizer, for example, is not really related to the Gaussian idea at all. So all of these tricks can translate to other embedding representations, which we also gonna see in ZIP-NeRF, which is not using the IP features but as they are, but they are using more of a hash grid trained features as input. Okay. Let's look at the limitations. Though Mip-NeRF 360 significantly outperforms Mip-NeRF and other prior work, it is not perfect. Some thin surfaces and fine details may be missed, such as tires, spokes, and in bicycle scene or other phase on the left in the strump scene. View synthesis quality will likely degrade if the camera is moved far from the center of the scene, and like most NeRF-like models, recovering a scene requires several hours of training, accelerator precluding on-device training. And this is the issue, that this is really slow still. This is like an old NeRFs very slow. Yeah, let's look through if there is like something very cool in appendix. Our model contains some of the small components not discussed in the main paper that improve performance slightly. Off-axis positional encoding. When constructing integrated positional encoding features, we must select basis P. In Mip-NeRF, this basis is selected as identity matrix, but this is convenient because it means that only the diagonal of the covariance matrix is required to construct IP features, and off-diagonal components need not be computed. However, the parameterization used by our model requires access to full covariance matrix, as otherwise Kalman-like wrapping we use should be inaccurate in the presence of high anisotropic Gaussians, which are frequent in distant parts of the scene. Okay, so given that we require to construct the full covariance matrix, we take advantage of the extra information presented therein and encode not just axis-aligned IP features, but off-axis IP features as well. Okay, as our basis P, instead of identity matrix, we use a large skinny matrix that contains the unit norm vertices of twice the selected icosahedron. Yeah, sure. When redundant negative copies of vertices are removed, for reproducibility of sake, the matrix is. So they provide this matrix here. These off-axis features allow the model to encode the shape of anisotropic Gaussians with a similar intuition at the random Fourier features explored by Tansik, which otherwise are indistinguishable using axis-aligned IP features, as shown in figure 8. Ablating these off-axis features reduces performance slightly, with SSM for bicycle scene falling from 687 to 664. So this is actually useful. The axis-aligned positional encoding used by Mip-NeRF does not capture the covariance of the Gaussian being encoded. Here we plot 3 bivariate Gaussians colored red, green, and blue with axis-aligned IPE and with our off-axis IP, and show that marginal distributions produced by projecting each Gaussian onto the basis are used by each encoding. Because these Gaussians have identical marginal distributions, Mip-NeRF's axis-aligned IP produces identical features, while the off-axis projections of our approach allow them to be disambiguated. Okay. So this one is different than this one, that's the point. Okay. Computing IP features with a large P matrix using the procedure described in NeRF, diagonal P sigma PT is prohibitively expensive. A tractable alternative is to instead compute the equivalent expression sum PT dot product sigma PT 0, where is an element-wise product. Okay, it's not dot product, it's element-wise product, and sum is summation over rows. Okay. With this small optimization, off-axis IP features are only modestly more expensive to compute than the axis-aligned IP features used in Mip-NeRF. Okay, that's cool. Linear algebra for you. Before sampling ray intervals from proposal weights W, we anneal those weights by raising them to the power. Dilation, we slightly dilate each proposal histogram before sampling it. This reduces aliasing artifacts, likely because the proposal MLP is supervised using only rays that correspond to input pixels, so its predictions may only hold for certain angles in a scene. The proposal network is rotationally aliased. By widening the intervals of the proposal MLP, we help counteract this aliasing. To delete histogram SW, we first compute P, where P hat WI over SI plus 1 is SI, giving us a probability density that integrates to 1 rather than a histogram that sums up to 1. We then delete by computing some bullshit where PS is interpolation into a step function defined by S. P plus S. Equation 13 can be computed efficiently by constructing a new set of intervals whose endpoints are sort, okay, and computing max of all intervals in that expanded set. After deletion, we convert the dilated P back into the histogram by multiplying each element by the size of its interval and then normalizing the resulting histogram to sum to 1. When dilating each proposed histogram, we set the dilation factor epsilon to a function of the expected size of a histogram bin. That is for each course to find a sampling level k, in which we sample n of k, find intervals from the course histogram, then process it. We compute the procedure product of all sample counts that produce level k and set epsilon to a fine function of the inverse of that product. That's some crazy ass bullshit. Yeah, I don't know what's going on here exactly, but my understanding is they have some problem with this proposal network, and they want the proposal network to be wider. So they have this strategy here that is gonna push the histogram, make it more wider. And they make it wider by thinking, okay, how wide is the fine layer, expected size of histogram beam. Inverse of that product, yeah. Sampling Mip-NeRF determines n fine intervals along each array by sampling n plus 1 distances from the coarse histogram weights and using these sorted sample distances as the endpoints of set of n intervals. This approach of using sample points for use as an interval endpoints can produce unusual results, as evidenced by figure 9. It effectively erodes the coarse histogram, as the samples are unlikely to span the extent of each coarse histogram bin. For this reason, we use a slightly modified resampling procedure. We sample n sorted values from the coarse histogram, and then we use the midpoints of each adjacent sample pair as the endpoints of our new set of fine intervals, and we reflect the first and last sample around the first and last endpoint to deal with the boundary conditions. This change has little quantitative effect on the random equality, but we found that it qualitatively reduced aliasing. Okay, so instead of doing this here, we just do this. Sounds good. And these are some more additional results. Okay, what is this implementation? This is bullshit. The Jacobian GF used by Kalman-like representation can be computed straightforwardly using most AutoDiff frameworks. A less expensive alternative, as it does not require the explicit construction of Jacobian metrics, is to instead construct and apply a function whose application corresponds to a matrix multiplication with G of GF. In JAX, this can be accomplished using linearized operator, applying it twice in a sequence to sigma with the dimensions of the current matrix transposed after each application. Okay, there is some additional trick for fast computation. Okay, so that's it, I think. So, quick summary of what happened here. So, Mip-NeRF 360 is an extension of the original Mip-NeRF model. The whole point of the paper is to reparameterize bounded 3D region into an unbounded representation that is actually fitting this bounded radius 2 ball here. And for that they provide their own contraction function that is pushing all the coordinates into this radius 2 ball, and they also provide their own distance metric S that is aligned with this contraction, so that objects that should be uniformly sampled can be uniformly sampled at S inside this ball. So this way they have this like reparameterization, but they also have to solve it not just for points, which would be more straightforward, but for the volumes, because they are using these IPE features that use the 3D Gaussian representation for encoding volume together with the positional encoding here. So they do that for the volumes, and they push the Gaussians to fit into this size 2 ball. And this way they can put in these IPE features from this ball into the NeRF MLP without the worry that the input is far away from the origin, right? So this is the way to make it unbounded. And then they introduce 2 more features to the whole project. So they come up with the idea of the proposal MLP. And find a NeRF MLP. So the idea is, instead of having one MLP and a big MLP that you evaluate 2 times, first in uniform fashion and then resampling on it, they have a smaller MLP, much smaller, about 8 times smaller, that is going to only produce the densities that align with the final big MLP that is gonna produce the vision reconstruction. And that's the second part. This is this part of the course to find online distillation, and this basically allows them to have much bigger main NeRF MLP while they train this proposal network just to approximate the histogram here. So that's the second main idea. And then the third main idea that they added is they have this new regularizer that they introduce here, that is pushing the distribution of the densities to be more of a step function. So this picture is best visualization they have for that. So this new regularizer is eliminating floaters effectively. They don't do this kind of what was previously done, this like no, adding the noise to the densities. That's what they did before, right? It's discussed somewhere here. Previously some results they added noise to the density to eliminate the floaters, so that they have to be around these points in densities. But that would make far away points very blurry. So instead they come up with this much smarter idea of just how do we force this mass of densities to be closer together in the 3D space. So this is how they do that, and this eliminates floaters very effectively, as seen here, right? So much better than this noise idea that was previously tested, this noise injection. So yeah, so they have these 3 components, and with that they arrive at much better state-of-the-art results than what was provided previously. Yeah, this is like a very, very clean results, but it's still very slow to learn, to teach, to train. Even though they created this proposal MLP, they more use it as a way to just be allowed to even have this big 8 layers made NeRF MLP, rather than just really increasing the speed of training. The speed is very slow still. It's not prohibitively slow, but it's very slow. So we will talk about ZIP-NeRF in the next live stream, where we will learn how do they increase this training speed extremely over this Mip-NeRF 360. But it was very interesting to see how they do the reparameterization of the scene. It was very cool to see this proposal network being introduced. And I think the regularizer actually is a very smart idea that can be applied to many more many more NeRF training procedures than just Mip-NeRF. So great paper. I think we will go to the ZIP-NeRF, which is building on top of the NeRF 360. So we will revisit many of these ideas in the next live stream. But thank you so much for watching. If you have any questions, let me know in the comments. I will try to get back to you. But I like the paper a lot, and it was fun reading it with you for the first time. So thank you so much. See you.